Hello and welcome to the lectures on power electronics. This lecture we'll be discussing about phase control rectifiers and the single phase semiconverter. Okay, so now let's see what is a semiconverter, a single phase semiconverter. Now semiconverter, it's a half control bridge rectifier. So we study about diode rectifiers, conventional diode bridge rectifiers, which give a constant output voltage. Semiconverter gives a variable output voltage. It has got two thyristors and two diodes and is connected in the conventional bridge configuration. So semiconverters are normally used where applications you require positive voltage, right? So positive voltage and basically rectifying action wherever rectify AC to DC you have and you require positive voltage, then you use the semiconverter. Now it is a one quadrant converter, which means that your voltage is constant, so voltage is positive and your current is positive, so that it works in the first quadrant. So which means that you can get an output voltage which is positive and an output voltage which is also positive, right? So it works in the first quadrant. Now let's see how the semiconverter works. Okay, now let's see what is a single phase semiconverter using a resistive load. Now, there are two configurations which we can speak about in the semiconverter. We have got a symmetric configuration and an asymmetric configuration. The symmetric configuration has two thyristors and two diodes. So this is connected in a normal bridge configuration like we connect for the diodes. So normal conventional diode rectifiers use four diodes and this configuration, same configuration. Here, instead of four diodes, we have got only two diodes and the remaining two diodes are replaced by thyristors, right? So this is called as a symmetrical configuration. Why? Because the two thyristors have got their cathodes common. So these two cathodes are connected to the point A, which is common. Now, this has got an advantage, symmetrical configuration. When the cathodes of the thyristors are common, it is easier to give the gate signal because normally the gate signal of thyristor gate signal is given between the gate and the cathode. So, if this is the gate, this is the G1 and G2. So, normally the gate signal, we have not shown the gate signal or gate pulse here. It is understood that it is given. But when you give this gate signal, it is to be given between the gate and the cathode. So since the cathode is common for both the thyristors, it's easier to give the gate signals. The second configuration is called as the asymmetric configuration. So you can see the difference here that the two thyristors are on the same leg of one bridge, of one arm of the bridge, sorry. So this is a bridge, this is the first arm and this is the second arm. So in this case, in the asymmetric configuration, both the thyristors are on one arm and both the diodes are on the second arm. Whereas in the symmetrical configuration, both the thyristors are on separate arms of the bridge. So you can see here again that in these case, the thyristors cathodes are not common. This cathode is connected to A and here this cathode is connected to this point. So the cathodes are not common. So when we are giving the gate pulses, it becomes a little more complicated in design, right? So the symmetric configuration is normally preferred and we will be seeing this in detail. Okay, so now let's see the semiconverter symmetrical configuration. So you have the AC input here and it is given across the terminals L and N. Now you can see that this is a symmetrical configuration, which means that the cathodes of the two SCRs are common here, like I said before. And because of which the advantage is that gates can be connected. So a single gate pulse can be used for triggering either SCR. So this is the advantage of a symmetrical configuration. So how is the circuit working? At any time, two of the devices are going to be conducting. Now, during the positive half cycle, we have the T1 and D1, which are forward bias, and they will be conducting. And but at the same time, we need the T1 is a thyristor, so it requires to be given a gate pulse. Similarly, you have to give pulse to T2 during the negative half cycle so that it will conduct along with D2. So T2 and D2 conducts during the negative half cycle. T1 and D1 conducts during the positive half cycle. So now let's see again how this is. Okay, so let's see the single phase semi-converter with R load at different instance. One is from alpha to pi and from pi plus alpha to 2 pi. So if you observe here, the conducting devices are going to be T1 and D1 during the positive half cycle. So during the positive half cycle, the L terminal is positive, N is negative. So the current flows from L through T1, through the load, through D1, and then back to the negative of the supply. So since we are speaking about the positive half cycle, so this is L terminal is plus and this is minus. So the current is like this, flowing through T1, through the load, and then through D1 and then back. So if I draw it, so this is going to be L, then this is thyristor T1, which I'm going to be representing by a short, because once it is in conduction, it is just like a short. And this is your diode D2 again, which is can be represented by a short when it is conducting, and this is your N. So current flows from the positive terminal of the supply voltage through the load. Suppose I call this load terminals as PQ. The current flows from P to Q through diode D2 and then back to the neutral, right? So this happens from alpha to pi because we are firing the thyristor T1 at alpha. Now what happens at from pi plus alpha? So what happens at for the AC cycle is like this. AC cycle is positive and negative. So from alpha to pi, your T1 and D1 are conducting together. Whereas at pi, the voltage becomes zero. Since it's a resistive load, the current also becomes zero, and the SCRs are reverse biased here. The devices T1 and D1 become reverse biased, and it will turn off at this instant. Now, since it's a resistive load, the concept is that voltage and current are in phase. When voltage is becoming zero, the current is also becoming zero. Through the thyristor, the current also becomes zero and the thyristor will turn off. Now, when the thyristor is turned off during the negative half cycle, now we are in the negative half cycle. Now, during the negative half cycle, it is thyristor T1 and D1 now have turned off, and we are going to be having T2 and D2. But T2 is fired only at pi plus alpha, not instantly at pi. It is triggered only at pi plus alpha. So till it is triggered, there is again no output across the load, right? So there will be no output till we fire pi plus alpha. So from your instant pi, so from pi to the next instant, so pi plus alpha if you call it as, from pi to pi plus alpha, no device is in conduction. From pi plus alpha to 2 pi, T2 and D2 will conduct together. So speaking about the waveforms of the output voltage, which appears across the load, the output voltage looks like this. This is how the output voltage looks like. So this is a semi-converter or a half-controlled converter. Why do you call it as? And this is a full wave rectifier. Now, what do you say? But a half-controlled full wave rectifier. So, what do you mean by a full wave rectifier? When you have an output in both the cycles, right? So, FWR is a full wave rectifier which gives you output during both the half cycles. So, normally if you have a diode rectifier, you have an output like this in both the half cycles. You are having a similar output in both the half cycle, but it is a little controlled, right? So you are having a waveform like this in the case of a semi-converter, where the control is with respect to alpha. So when we are giving the firing pulses, so now observe these waveforms. At alpha, the firing pulse is given to thyristor T1. Similarly, here it is pi, and we call this interval as pi plus alpha. So this is alpha, pi, pi plus alpha, 2 pi, and so on. At alpha, the thyristor T1 is fired. So again, we saw the working. The T1 is fired at alpha. So T1 D1 combination works during the positive half cycle. So the voltage across the load is going to be nothing but VLN. Now, if you observe this, this is the supply voltage which is given. So supply voltage VLN and VNL are both drawn over here. So if you observe this here, uh, this is VLN. When this is positive, the VNL, this is VNL, this is negative. So we can say this is VNL. So during the positive half cycle, when T1 and D1 are conducting, so keep this in mind, when T1 D1 combination conducts, the output voltage or the load voltage is going to be equal to the voltage VLN, and when this is when T1 D1 conducts. When T2 D2 conducts, your output voltage is going to be equal to NL, right? Now, this is during the negative half cycle I'm speaking about. So, negative half cycle, the current flows from N through T2, through the load, through D2, and then back to L. So, N is positive with respect to L. So, this is our negative half cycle. So, negative half cycle means VNLN is negative, but VNL is positive. And when we are firing the thyristor T2 at pi plus alpha, so at pi plus alpha, you have again a firing pulse, given. So T2 and D2 will conduct together, and we are getting an output across a load which is nothing but equal to VNL. So the load waveforms are redrawn over here. So from 0 to alpha, there is an output voltage which is shown here. This is from 0 to alpha. T1 and D1 conducts, and the output voltage is like this. From pi to pi plus alpha, there is no output voltage because none of the devices are conducting. T1 and D1 turn off at this instant pi. T2 is not fired till pi plus alpha. So none of the devices are conducting. Output voltage is equal to 0 here. And from pi plus alpha to 2 pi, again T2 D2 combination conducts. And again the voltage across the load is equal to the supply voltage, but now it is equal to NL instead of NN. Okay? And VNL is positive at that time. So which means what? Your output is average, output is positive. Right? So these are the waveforms for the semi-converter. Let us derive the expression for the average and RMS voltage. So first let us draw the waveform of the output voltage, right? So from 0, when you're drawing, it is easier if you mark. So 0 to alpha, this is how your output voltage is. And again from pi plus alpha to, so this is pi plus alpha, this is pi, and this much is your output voltage. So this is basically how your output voltage is waveform is going to be looking like. Now we want to derive the expression for, so this is my output voltage across the load, right? So output voltage across the load is going to be VO, right? So this is omega T, and I'm going to be deriving the expression for the average value. So your output is DC. So average value is the DC value, and this is given by, normally we find out the average value by integrating over the whole period, integral over 0 to t of your whatever voltage is, right? So here if you are considering what is the period in this kind, in this waveform, the period is equal to pi. So it is repeating after pi. So period is pi. And from 0 to alpha, there is no output. So from alpha to pi, we have got, and the waveform is Vm sine theta d theta, or Vm sine omega t d omega t, right? So 1 by pi integral alpha to pi of Vm sine theta d theta. And when you integrate this, you get the expression, it is equal to Vm by pi into 1 plus cos alpha. This is called as the average value, or the DC value of your semi-converter. So this is the average output voltage. The value Vm by pi into 1 plus cos alpha. So what can you understand from this? the average value when alpha is equal to 0. So alpha is equal to 0, your output voltage VDC is equal to 2 Vm by pi. When alpha is 90 degree, it is Vm by pi, and when alpha is 180 degree, it becomes equal to 0. So when alpha is equal to 180, your VDC becomes equal to 0. So this is how the variation of your output voltage is. It is maximum at alpha is equal to 0, and at alpha is equal to 180 degree, it becomes equal to 0. So this is 2 Vm by pi, this is 0. This is your variation of output voltage. So on the y-axis, I have plotted VO, and on the x-axis, this is alpha. So with respect to at pi, the output voltage becomes 0. So it is always positive. So output voltage is always positive. So the semi-converter is called as a, we call it, the current direction is always positive, and we call it as a one quadrant converter. Like I said, voltage is positive and current is positive. So this is the expression for the average voltage. Now similarly, if I want to find out the RMS value of your output voltage. Now RMS value is what? Root mean square. Root of the, so take the square root of the mean. Again, mean is integrating over the period. Root of the mean of the squares. So what is the square? It is Vm squared sine square theta d theta. So square of Vm sine theta d theta. So root of mean of the squares is taken. And when you are doing this, you can integrate it. You can use sine square theta as 1 minus cos 2 theta by 2, put the limits and integrate. You will be getting an expression like this. Vm by root 2 into 1 by pi into pi minus alpha plus sine 2 alpha by 2 the whole raised to half, or square root of this. Right, so this is the expression for the RMS value. So what do you mean by the RMS value? Obviously, even though this is a rectifier which gives output voltage which is DC, still there is some AC component in it. So the AC component will be expressed by the total AC component that is expressed by the RMS value. So you may be asked to find out the average and RMS output voltages. So this is average value is nothing but the DC value, and RMS value is basically the AC value, right? Now let us consider the case of a single phase semi-converter with RL, or an inductive load. So initially we had seen the case with a resistive load. Now we are considering the case with an inductive load. So assuming a very highly inductive load, we'll say what is the significance of this. So normally semi-converters, single phase semi-converters are examples. So an example of an RL load is a motor. Motor has got windings and resistance. So resistance is R, and L is the winding, inductance of the windings. So semi-converters with RL load we are going to be seeing. So what is the difference is that the circuit diagram remains the same, but now we have an inductance along with the resistance for the symmetrical configuration. This is like this. Now, how do you work? So what is the basic difference when we have an inductive load? Now let us try to understand this. So we are firing at alpha, we are firing the thyristor T1. So from alpha to pi, the combination of T1 and D1 will conduct like as usual. And the output voltage is going to be equal to the supply voltage. Yes, we know this. Now what happens at pi? So we have the supply, this is your supply voltage, and from alpha to pi, so we are firing the thyristor over here, firing pulses. This is pi, then this is pi plus alpha, and so on. So pulses are coming like this. So the output, like in the other case, your output voltage is going to be equal to, so this is T1 and D1 conducting. This is from alpha to pi. Now what is going to happen at pi? The problem is we have got an inductive load here. Now an inductive load has a property that, and we are speaking about a very highly inductive load. Now, when we have an inductive load, the current through an inductance cannot instantaneously change. So, through inductor, the current does not change instantaneously. So, what does it do? It cannot suddenly become zero. Current cannot become zero instantaneously. What is happening at pi? At instant pi, this is alpha and this is pi. At instant pi, the voltages become zero and the current, the thyristors T1 and D1 are now reverse biased. So we are at the negative half cycle now where L is negative and N is positive. Now what is happening? So T1 and D1 were conducting. We have reached here. Now so what happens to the current through the load? The current was flowing through the load like this. So voltage has become zero. So now, and the thyristors have become reverse biased. So it is trying to turn off. But the current through the inductor, it is an inductive load. The current through the load cannot become instantaneously zero. So it has to find a path. So what does it do? The inductor has a property. So using Lenz's law, it induces an opposite polarity voltage like this. So when the current was initially flowing, this was plus and minus. It becomes reverse. So inductor induces an opposite polarity here. Now this polarity is a large polarity LdI by dt. A high LdI by dt is induced across this load and this is going to forward bias the thyristor again. So thyristor, if you see, the thyristor cathode is at negative again. Now through the load this point is positive. Now at instant pi this diode has become forward biased. At pi, D2 has become reverse bias, so it turns off. Sorry, D1 has become reverse bias, so it turns off. But D2 is forward bias now, and it can conduct, right? So now, as the load induces an opposite polarity here, D2 is anyway forward bias, and T1 anode also gets a positive. So which means what? T1 anode is at positive, cathode is at negative. T1 remains in conduction, and the load current is going to be flowing through this path through T1, through D2 and through the load and it keeps circulating like this. So what is happening here is that from the instant pi to pi plus alpha. Now pi plus alpha, what is happening? You're going to be firing T2 again. So T2 and D2 will come into conduction like before. But from pi to pi plus alpha, we have the combination of T1 and D2 conducting. And this phenomena is called as something called as freewheeling. Now what is freewheeling? Let's again see this in detail. Semi-converter with RL load, there is something called as freewheeling. So during the freewheeling period, so what is freewheeling period? There is no current through the supply. During the time alpha to pi, the inductor had stored energy. So from alpha to pi, T1 and D1 were conducting. So positive half cycle, T1 and D1 were conducting. The inductor stores energy. Now at pi, what has happened? D2 D1 will turn off, right? Because it is in the negative supply. So negative half cycle has started. So now this was initially, this was positive and this was negative and T1 and D1 were conducting together. After that, we have reached the negative half cycle. So from alpha to pi, it is T1 D1 combination conducting and output voltage is equal to the supply voltage. At pi, what happened? Your negative half cycle has started. So it is like this. So this is your pi. Negative half cycle has started. So T1 should ideally it is reverse bias and it should turn off. But the problem is that we have got an inductive load. The current through the load is trying to become zero, but it cannot instantaneously become zero. So this current will continue flowing through. Now D1 is reverse bias and it turns off. But D2 is forward bias. So this current will find a path through D2 and through T1 and then it will continue circulating. So it is like this. T1 and D1 will be connected basically across the load. So this is your L and this is R and this is T1 and T2 combination. So since we are considering these, if you consider them to be ideal switches, it's like a short across the load. So effectively, you have got, when they are conducting, this is the load terminal, the whole. So let us consider it as PQ. The load voltage is across PQ. RL is a load. Across the load, we have got a short when these two devices are conducting. So what is your output voltage from at pi to pi plus alpha? Output voltage. So we have got the condition, sorry, T1 and D2 conducting, output voltage is equal to 0. So T1 and D2 are conducting and output voltage is equal to 0. Till at pi plus alpha. So at pi plus alpha, we are going to be firing T2. And now T2 and D2 will conduct together. Again, output voltage is equal to Vs. So during the negative half cycle, so now we have reached pi plus alpha. We have started. So the condition is that at alpha we are firing T1 and D1. Sorry, T1 we are firing and T1 and D1 will continue together. The load stores energy. At the pi, the voltages become 0, but the current cannot immediately become 0 because it's an inductive load. So the load induces an opposite polarity voltage. Now that opposite polarity voltage will be the like this. So it is going to be minus and plus, or you can show it here, minus and plus. And this is going to be forward biasing this thyristor. The cathode is at negative, the anode. So once this is conducting, this is a diode. It is conducting, it is like a short and it is connected to positive. So effectively the anode of thyristor T1 is connected to positive, cathode is connected to negative. So T1 and D2 are remaining in conduction. T1 is forward biased and it will remain in conduction. So the current through the load is going to circulate through these devices like this. At this time, the supply is not connected, or the supply current, we can say it is equal to 0. There is load current. So we can say there is load current is there, IL is there, IL is there, but IS is equal to 0. So the supply current is off during the freewheeling period. The same thing will happen at, so we spoke about alpha, pi, then pi plus alpha, and then at 2 pi. So this is pi plus alpha and at 2 pi. So at 2 pi, what is going to happen? Again, the same thing. T2 and D2 were conducting together. The load was storing energy, but at the 2 pi, D2 will turn off and then D1 will come into conduction. So T2 will continue to conduct along with D1. So it is going to be T2 and D1 combination. So let's observe the waveforms of the semi-converter with RL load. Let us now observe this. If I see from alpha, if you observe this output, the output looks very similar to that of the semi-converter with resistive load. So you from 0 to alpha, output voltage is 0. From alpha to pi, that is equal to the supply voltage. Pi to pi plus alpha, again it is 0 and so on. But what is different is that the conducting devices are different. So if I show, so your conducting devices are T1 and D1 during alpha to pi, then T1 continues from pi to pi plus alpha, but along with D2. So T1 D1, then T1 D2, then T2 D2, then T2 D1, and then again T2 D1, and it continues, right? So the same thing, since it's continuous, so it is still, we are assuming continuous conduction is there. So now if you observe the waveforms here, this is for the output voltage. So again, main difference. So if I draw the output waveform here, and so on. This is alpha, this is pi plus alpha, this is 2 pi, and so on. So in this point, it is T1 and D1, then it is T1 and D2, then T2 and D2, then T2 and D1, and again it continues. So from here also it will be T2 and D1. This is what is shown over here. So if we can see the average output voltage waveform nature is the same, but the device conduction in the resistive load case, there were no devices which were conducting during the pi to pi plus alpha period. All the devices were off, so output voltage is 0. Now output voltage is 0, but the devices T1 and D2, they are in conduction and there is load current. The current is always there. So that is the difference, that output voltage is equal to 0, but output current is not equal to 0 in this case with the inductive load. Now we are assuming here, if you see, the load current is shown as a straight line. Actually, it is slightly of a nature. It's not exactly like this. The load current is storing energy, so the current increases. Then when it is during the freewheeling period, the load, whatever energy it is stored, it is dissipating or circulating through the thyristor and the diode combination. So it will decrease. But before that, again the next cycle starts, and this and the storing again starts. So what we see is that your average value is approximately, it's a constant, and we are speaking about small alphas here. So here we can see that the almost constant continuous current is there. So this is what you mean by continuous current. There is always current through the load. So it is denoted by a straight line. So this is the load current. Next, waveforms which we are drawing is, let us observe the current waveform. Right now, from alpha to pi. So basically, again, redrawing the or showing the circuit here, we can say these are the devices T1, T2, again D1 and D2, and these are the supply terminals, line L, N, and this is your load. Now, so we know that from alpha to pi, the current was flowing. So whenever supply current, how do you draw the supply current? Supply current is there when it starts from L, goes through the devices and returns back through N. So N is a return path. So we consider that to be positive. So if the current starts from L and returns through the negative, that is N, then supply current is, we consider it to be positive. If it starts from N like this, if the current starts from N and then returns to L, then the current is supposed to be negative, right? So when T1 and D, so this is T1, D1, T2, D2, sorry, T1, D1, T2 and D2. So when T1, D1 conduction is happening, the current is flowing from, so that is during the positive half cycle. So the current is flowing from the positive L through T1, through the load, through D1 and back. So from L through T1, through the load, T1 and back. So at that time, we say that the current is positive. And what is the magnitude of the current? The current is flowing through the load only. So it's basically the load current only, what is flowing through the supply. And what is the load current? We are assuming it to be a constant. So the magnitude of the supply current will be the same as that of the load current. So from 0 to alpha, so we'll consider from here, let us start from here. At alpha, when you are firing T1, so T1 and D1 continuing together, the supply current is positive and magnitude, maximum magnitude is equal to the load current, because the supply current is actually flowing through the load and then returning back, right? So the magnitude of the supply current is equal to the load current. So from alpha to pi, this is the state. Now what happens at pi? At pi, your D1 has turned off and the load current is basically circulating through the devices T1 and D2. So we said that was freewheeling. And during freewheeling, the load has whatever energy it has stored, it is just circulating through these devices, but there is no supply current. Supply current will be there, like I said, only when T1 D1 combination is there or T2 D2 combination is there. Otherwise, there is no supply current. So the supply is cut off. So that is why the current becomes equal to 0 here. So this is the supply current, which is 0 from your pi to pi plus alpha. So let us mark it out here. This is alpha. This is pi. Pi plus alpha, 2 pi. Here we have the devices T1 and D1 conducting. So like I said, T1, D1 conducting, supply current positive. When T2, D2 are conducting, supply current is negative. And when T1 D2 combination, that is whenever the on the same leg of a bridge, so this is the arms of the bridge. This is one arm, this is the second arm. So on the same arm, if the devices are conducting, it is just like a short across the load. So output is equal. There will be current, but the output voltage will be zero, and there is no supply current because the supply current has to find a path. So there is no path for the supply current to start and end, because we have got only T1 and D2 in conduction, not T1 and D1 combination or T2 and D2 combination. So supply current is equal to 0 at this instant. So from alpha to pi, supply current is positive. From pi plus alpha to 2 pi, when T2 and D2 are conducting, supply is negative. Magnitude is going to be equal to the load current. Same value, but only the direction has changed. So now the current is flowing from N through the load and then back to L. The direction has changed, right? So direction has changed during the negative half cycle, I'm saying. So during the negative half cycle, this is positive and this is negative. So the current is going to start from the neutral N terminal through T2 and load, and then back through D2 to L. So the current direction reverses, and that is why this has become this has become negative. The supply current has become negative, right? So this is how you draw the waveform of the supply current. Now the next is the waveform of the voltage across a thyristor. Suppose you are asked to draw the voltage waveform across the thyristor. Now how do you understand this? Whenever a thyristor is conducting, so Vt, whatever thyristor it becomes, when Vt is on, the voltage is equal to Vt will be equal to 0. When thyristor is on state mein, Vt becomes equal to 0 because it's like a short. When Vt is off, or sorry, when the thyristor T1 is off, Vt1 or the voltage across it, it has to withstand the whole supply voltage, that is equal to the supply voltage. So from here to here, if you see from 0, let's see, from the thyristor T1, just observe the conduction period. So it is written over here, T1 is conducting from alpha to pi plus alpha. It is starting to conduct from alpha. It is conducting along with D1 till pi. Then from pi to pi plus alpha, it is conducting with D2. So whatever it is, T1 is conducting from this period alpha to pi plus alpha. So which means that from alpha to pi plus alpha, your voltage across the thyristor is equal to 0. So when a device is on, the voltage is equal to 0. That is what we are showing. So when T1 is on, from alpha to pi plus alpha, the voltage across it is equal to 0. Now before that, the supply is positive here, right? When the thyristor is off, it has to withstand the supply voltage. So what will be the voltage across the thyristor? It will be just the supply voltage. Supply voltage is positive during that instant. So the whole supply voltage appears across the thyristor. Then it turns on, so the voltage becomes 0. Now at this instant, the supply voltage, now at pi plus alpha, what is happening? T2 is turned on. So T1 will turn off, and again when it is off, the voltage should be equal to the supply voltage. What is the supply voltage at that time? It is in the negative half cycle, right? This is the supply voltage and this is the negative half cycle. So negative voltage will be appearing across the thyristor, and then the remaining part will be there. So this is how the waveform across the thyristor can be drawn. So keep this in mind. Just see the instance at which the thyristor is conducting. When the thyristor is conducting, its voltage drop is equal to 0, assuming that it is an ideal device and it works like a short. Actually, there will be practical drop or whatever the device is corresponding to that. But if you are assuming it is ideal, then the voltage across the thyristor is 0. Right? Then thyristor T1 is off, then VT1 is equal to. So whatever the thyristor be, if it is VT2, so we see when T2 is conducting. So from here to here, T2 is conducting, the voltage across it will be 0. And when it is off, whatever will be the supply voltage, whether it is positive or negative, that will appear across the thyristor. So this is how you draw the waveforms Okay, so we saw the semi-converter with symmetrical configuration. Now this is a asymmetrical configuration. Asymmetrical configuration is not commonly used because, like we said, here the cathodes of T1 and T2. So asymmetrical configuration is when T1 and T2 are on the same arm of the bridge. D1 and D2 are on the second arm of the bridge, right? So the problem is that T1 and T2 cathodes are not common. So gating or the giving gate pulses becomes difficult and complicated. So this is rather not much commonly used, but still, just to see the how it with the resistive load, how does it behave? T1 and D2 will conduct together. So all this, the main difference is in the how the gating pulses are given. But otherwise, once it is given, T1 and D2 combination will continue during the positive half cycle from alpha to pi. Then from pi plus alpha to 2 pi, it will be T2 and D1 conducting. The output voltage waveform looks exactly the same, right? So this is so resistive load does not much change, and the output. So waveforms for the asymmetrical configuration also are actually like this: alpha, pi, pi plus alpha, and 2 pi. So this is what. So since this is a resistive load, the current can immediately. So when your negative half cycle starts, the current immediately becomes zero, and the thyristor T1 will turn off until T2 is fired during the negative half cycle at pi plus alpha. Your there is no output voltage across the load. So this is what the asymmetrical configuration. Symmetrical configuration is more important and commonly used. So we have focused only on the symmetrical configuration. So to conclude, the single phase semi converter we have discussed with R and RL load, both cases. We have also seen how to derive the to draw the waveforms. Then we saw the concept of freewheeling in RL load. So this is only in the inductive load that the concept of freewheeling is there. Two configurations, symmetric and asymmetric configurations, how to draw the waveforms, and also the derivation of the average and output voltage for the semi converter. This has been discussed.